Alright, so we're going to go ahead and do number 9 here, and basically doing the same thing. The only difference is we're supposed to use the first derivative test to see if it's a maximum or minimum, and basically we're doing the same thing here. It's going through really quickly, but just setting it equal to 0 and solving, okay? The same thing we've done a lot in the past. We find that x equals 1 is the critical point after setting it equal to 0, okay? And then the first derivative test basically is this derivative tells us if the derivative is positive, that means the slope is increasing, and if the derivative is negative, that means the slope is decreasing. So you can plug in a point, like points right around 1 that are just like 1 higher than 1 and 1 lower than 1, and when you do that, basically, like if you plugged in 0 to this, then you'd get a certain value. I think actually it would just be 0. Well, you could plug in like 0.5 or something, and then you could plug in 1.5, which are values right around 1, and then you could see if it came out with a positive number, then on one side of 1, and a negative number on the other, then that would tell you if it's, increasing or decreasing. So for example, we have the graph here, the graph of this function, because you're supposed to see, supposed to use the graph to check your work, is what it says. So we have the graph of this function is something that looks kind of like this. And so this is 1 because of course we have that critical point right here at 1. So this is just the graph of the function. I graphed it, I looked it up, and from here you can see that it's a minimum, obviously, because it's down at the bottom of the crest. But if we were to look at the slope, see how the slope is negative right here before it, and then after it it's positive. It's like increasing, it's decreasing here, and then it's increasing. Well, like I said, if we were to plug in, because the derivative, if the derivative is negative, it'll tell us that the slope was decreasing. So I guess if we would have plugged in like 0.5, it would have been a negative number, which told us that the slope was decreasing. And then if we plugged in 1.5, it would have been a positive number, and that would have told us that it was increasing after 1. So if you can picture it in your mind without even having to draw the graph, if you plug in 0.5, a number right before 1, and get a negative number in the derivative, you plug it in here and get a negative number, then you know it's decreasing. And then if you plug in a number higher than 1 and it's a positive number, it's increasing. So if it goes from decreasing to increasing, that's forming kind of a valley, then it's a minimum. And if it's going from a positive number to a negative number, it's going from increasing to decreasing, and then it's a maximum. It's at the top of the value. Alright. Alright, so we have number 17 here. And number 19. So basically what we're asked here is to see if we can find a critical point, if it has a maximum or a minimum, right? So we look, and number 17, it does, it's at x equals 0, obviously, and that's a minimum, and we can see that pretty clearly from the graph. Number 19 has 2, we have a maximum and a minimum. Pretty easy to see that the maximum is at -1, but the minimum, I couldn't tell if that was at 1 or 1/2 because of the way it was labeled. Kind of looks like it's at 1/2, but I'm not too sure. It just depends on the way it was labeled. But we can move to number 21, A. If B is a positive constant, find all the critical points. So again, all we have to do is take the derivative here. So we take the derivative, set it equal to 0. We set it equal to 0 down here, but we also know that x equals 0 is a critical point because x is on the in the denominator there, and whenever that happens, you can't have it equal 0, or else it would be undefined. So at that point, that's when obviously we have a critical point. So then we set it equal to 0 and solve, and when x equals b is when we have those other critical points. So there we go. That's number 21a. Again, just finding critical points after taking the derivative and setting equal to 0, or finding where it's undefined. Okay. So now we're going to do part B. Use the second derivative test to determine whether the function has a local max or local min at each critical point. So the second derivative test, you basically take the second derivative and then plug in those critical points. Okay. So we plug in the critical points to x, and we solve. We plug them into the second derivative for, we basically, these are the critical points here, and one by one we plug them into here because that's the second derivative. And once you plug them in, if you get a positive number, then the slope is increasing, and if you get a negative number, the slope is decreasing, I believe. Okay. Alrighty. So number 23, here we go. Very similar again. You just have, instead of numbers, they're just putting in letters. Nothing's changed. It just might get a little confusing with the letters in there, but treat them as if it were like a 2 and a 3 or something. So you take the derivative again. You find, set it equal to 0. Find its critical points, and that's basically it. So we solve here, and I do make one mistake right here when I divide by v coming up. You have to basically divide by e to the t, so you can get the stuff, things on both sides, and then divide by v so you can get that on one side. But this should not be multiplied. This should be over v. Okay. So then you have u over v, and you can solve for t from there. You can take the natural log, and you take the natural log of both sides to get t to the bottom and whatnot. But I want to challenge you to try to solve for t from there to see what the critical points are in terms of u and v, because you're just treating these things like numbers. It's as if it were like a 2 and a 3. It's nothing different than what we've been doing. Okay, it's just a little harder to solve for t, and it's also a little harder because these are letters instead of numbers, but it's the same thing.